This is 8, 4, right? So 8, 4, we had our 30, 60, 90 triangles and our 45, 45, 90 triangles. That's like the reference material you would have needed for 8, 4, 45, 45, 90 is A, and A root 2. And then 30, 60, 90 is A root 3, and 2A. So for 1, 2, and 3, well, just specifically for just 1, this would be A, and A root 2. So each of these is going to give you a little bit of different pieces of information. Number 1 gives you that R is 6. So if this is 6, then this is also 6. And this would be 6 root 2. So T is 6 root 2. For 2, it gives you that S is 2 root 5. So if S is 2 root 5, so is R. And then this would be 2 root 5 times root 2. When you've got two numbers that are underneath the square root, you multiply them together, and I'd get 2 root 10. And root 10 can't be simplified, so it would stay as that. Then came 3. T is given 2 this time, so T is 10. So when I'm given the A root 2 side, I've got to divide both sides by root 2. And I get A is 10 over root 2, which has to get rationalized by multiplying by root 2 in both the top and the bottom. And I get 10 root 2 over 2, which reduces to 5 root 2. So both S and R would be 5 root 2. And again, we're keeping these exact, so keep that in mind that these are kinds of questions on your test that are going to be kept exact. And the format on these, like if it was multiple choice, obviously you'd see it. But if it was open-ended, it's going to say 6 square root SQRT and then 2 in parentheses for whatever's underneath the square root. So this is how a fill-in-the-blank question would be answered. Questions on any of those? So your 45, 45, 90. Okay, then 30, 60, 90 is the next chunk. So opposite the 30 is your A, opposite the 60 is your A root 3, and opposite the 90 is your 2A. For number 4, they give me Q is 8. That's my opposite 30 side. So then P is 8 root 3, and N is 2 times 8, or 16. I'm just going to redraw it down here. So 30. 60, 90, A root 3, 2A. So for number 5, N, which was down here, the hypotenuse, is 20. That's my 2A side. So I'm going to divide both sides by 2, and I'm going to get that A is 10, which means the opposite to 30, which is your Q, is 10, and opposite to 60 is 10 root 3. One more time. This is again A root 3, 2A. So this time they give me P. P is 4 root 3. So if A root 3 equals 4 root 3, and I want to get A by itself, I would divide both sides by root 3. And they're going to cancel, and A is 4. So this one is 4, that's your Q, and this is 2 times 4, which is 8. Questions on anything relating to 8, 4? So the only other thing really we saw was like a square with a diagonal or an equilateral triangle with an altitude, which makes the square becomes the 45, 45, 90, the equilateral becomes the 30, 60, 90. Everybody's good? 8, 4? Yep. Okay. Game 8, 5. So 8, 5 was tangent. So I'm going to write this because they are all going to get blended in together. It's not going to tell you. This is 8, 5, so you know it's tangent. You've got to know how to set it up. Notice this said round to the nearest tenth. All of these require a calculator. So if I want to solve for x here, x is opposite the 35, 10 is adjacent to it, so I'd get the tangent of 35 equals x over 10, and when the number's in the bottom, I just multiply. So 10 times the tangent of 35 7.0. So I can keep it as 7 or I can do 7.0 either way. It's right. Number 2, 21 is here. The 30 is the opposite. So the tangent of 21 equals 30 over x. When the variable is in the bottom, I take the top number and divide it by the tangent. So x equals 30 divided by the tangent of 21 is what I want to type in the calculator. And I get x equals 78.15, so 78.2. Be really careful on your rounding. Then 3 and 4, oh, this should have a degree symbol on it, is missing the angle. So remember, when we're missing the angle, we're using the inverse trig functions. So I'm using tan -1. So opposite y is 8, adjacent to it is 5, which means the tangent of y is 8 over 5. And I would write tangent -1, 8 divided by 5 in my calculator. And I get 57.99, which rounds to 58 degrees. And then 4 gives me all 3 side lengths. So I'm going to use tangent because we've been consistent, but you could actually use any of the trig functions. I could have said the tangent of y equals opposite adjacent, so 6 over 8. I could have said the sine of y equals 6 over 10. And I could have said the cosine of y equals 8 over 10. And then I could have used any of those inverse functions. So I'm going to use tangent. Second tangent, 6 divided by 8 is y equals 36.86, so 36.9 degrees. And I would have gotten the same answer from each of those other ones. Sine -1 of 6 divided by 10, same answer. Cosine -1 of 8 divided by 10, same answer. The reason a lot of times they'll give you 3 side lengths like this is it won't give you the right angle. So the 3 side lengths, 6, 8, 10, are a triple, and what that tells you is that this is a right triangle. So sometimes you'll leave off the right angle, and again, trig only works on these right triangles, or SOHCAHTOA only works on these right triangles. So it's giving you all 3 side lengths so that you can state that it's a right triangle. Everybody good so far? Still with me? Yeah? Okay. All right, again, I'm going to write the word SOHCAHTOA at the top because we still need it. Okay, 8, 6. So now this was sine and cosine. So notice that there's 2 variables on number 1. It wants you to, and again, nearest 10th, pay attention to the rounding. Let's say I want to solve for x first. I want to use the information that they gave me at the beginning, which is the 56 and the 12. So x is opposite, 12 is the hypotenuse, which means this is sine. Sine of 56 equals opposite over hypotenuse. Numbers in the bottom, so I multiply. So 12 sine 56 is 9.94, so 9.9. Now I could use the Pythagorean theorem now because I have 2 of the 3 sides, but it's going to be less accurate because I just rounded that 9.9. So I'm going to stick to the information that they gave me. I'm going to use the y and the 12. In respect to that 56, y is adjacent, 12 is the hypotenuse. So I'm going to say the cosine of 56 equals y over 12. Multiply 12 on both sides. And I get 12 cosine 56. X is 6.7. I'm sorry, y is 6.7. And you can check it using the Pythagorean theorem. It's not going to be exact because we rounded it, but it should be pretty close. Okay, now I'm going to go to 2. Same thing, I have 2 variables. Let's say I want to solve for a first. 25 is opposite the a. 20 is the hypotenuse, so the sine of 25 equals a over 20. Numbers in the bottom again, so 20 times the sine of 25 is 8.45, which is 8.5. B is adjacent to 25. 20 is still the hypotenuse, so cosine 25 equals b over 20. Numbers in the bottom, so I'm going to multiply it again. 20 times the cosine of 25. 18.12, so 18.1. And then the last one on this one, again, looking for an angle this time, so I know it's the inverse buttons. 5 is opposite, 10 is the hypotenuse, so the sine of x equals 5 over 10. I do sine -1, 5 divided by 10. And I get 30 degrees exactly. There's quite a few questions from these two, like where you're having to solve for a triangle, so make sure that you're good on these. Questions? Thumbs up if I'm good to go to the next one. Okay. Last one was your word problems. The good news is there's only one word problem on your test. So application of the SOHCAHTOA again. From the top of a lighthouse, 20 meters high, a sailboat is sighted having an angle of depression of 4 degrees. How far from the lighthouse is the boat? So I've got a lighthouse, right? And then I've got a boat. And it says from the top of the lighthouse, 20 meters high. So there's the height of the lighthouse. It's cited as having an angle of depression. So remember, depression is eye level or horizontal down, which means my angle of depression is here, 4 degrees. And it wants to know how far is the lighthouse from the boat. So there's two ways to do this. One is make your right triangle on the bottom here. This would have to be a right angle. So if I did 90 minus 4 degrees, I'd get 86 degrees in here. And then I can use that angle. The other way to do it is 4 and this angle down here on the bottom are alternate interior angles. So I could put the 4 degrees here. So I'll set up both ways. If you use 86, x is opposite, 20 is adjacent, so I'd get the tangent of 86 equals x over 20. And in the calculator, I would type 20 tangent 86. And I get 286.01. It will tell you what to round to, but let's just say nearest whole number for now, 286. If I used the 4 degrees, 20 is opposite, x is adjacent. So tangent of 4 would equal 20 over x. Numbers in the bottom, numbers in the top this time, so I take the 20, divide it by the tangent. And 20 divided by the tangent of 4 gives me that same answer. And then the unit would be meters. So on your test, you won't keep your meter, you won't keep units. It's not going to ask you to type in your units, but just keep that in mind that like if it was a standardized test, you might pay attention to units because one might be in meters, one might be in centimeters. You want to just make sure that you have that accurate. But on today's test, if it was open, fill in the blank, you would just write 286. All right, questions on any of the warm-ups? Okay, so here's the solutions. Oh, it's sloppy, but they're there for 8-4. So we did what we did we did number 2, and then we did 10 and 12 together, but the other ones are there. For number 4, you should have gotten 3. For number 6, you should have gotten root 7 and root 7. And for number 8, you should have gotten 5 root 2 over 2 for both of those, because that's 45, so they're both the same. For 10, E is root 3 over 4, and F is 1/2. We worked through that one, and we worked through 12, right? 2 root 3 and 4 root 3. 14 is 13 over 2 and 13 over 2 root 3. And 16 is 3 root 3 and 9. $18 is 16 root 2. 20 is 5 root 3. Then 22 got a little tricky because it was right triangle within like your 30, 60, 90. So there was 3 different triangles actually, if you count the big one happening there. X should have been 3, Y should have been 9. If these got you, I wouldn't stress about it too much. Your test is more like the top part. But this is great application of what we knew. 24, X is 3 root 3, Y is 9. And 26, X is 10, Y is 4 root 2. Questions on those? Okay, this is 8, 5, which was tangent. Okay, 2 is 23.6, 4, 1.4, 6, 3.3. 8, 28 degrees. 10, 37 degrees. 12, 56 degrees. The degrees will also not be part of your answer. So when you go to answer this on if it's open-ended, it would just be 56, like not 56 degrees. Yep. Yep. Yeah. You're welcome. 14, W is approximately 286, and Z 571. 16, W 82, Z 154. And 18, again, a little bit trickier because there's multiple triangles happening there, but W is 520 and Z is 480. So this is a great SAT question. Your test is going to be more on level with the top of this stuff and like the ones in the warm-up. Questions on that one? Okay. 22, 44 degrees and 136 degrees, and 24, 28 degrees. So remember, a rhombus and a rectangle's diagonals meet at a right angle. That's why these work that way. You can't do this with like a parallelogram. They don't meet at a right angle. But these two, what's special about them is that they, actually not the rectangle, the rhombus, the diagonals meet at a right angle. So when you have the rectangle, you're using this right angle, right? Which is, so if it was like 20, 20 and 80, then you can use that right angle. And if you're doing a rhombus, they're all congruent, whether it's like that or like this. And their diagonals are perpendicular. So the rhombus right triangles happen inside the four corners, whereas a rectangle, this is so sloppy, but a rectangle happens with half of your rectangle. So a little application of those quadrilaterals that aren't going to go away. Questions on those? Last one, well, no, this is second to last one. 8, 6 was your sine and cosine. So 2x is 102, y is 64. Notice it said nearest integer, that means nearest whole number. X for number 4, 54, y 64. 6, x is 20, y is 20. 8, v is 67. 10, x is 9, v is 42. 12, x is 20, y is 10. 14, 83 meters. 16, 350 meters. So this got into a little bit of the word problems, except it gave you the diagram. What's the difference? Your test, you're going to have to draw your diagram. Questions on those? All right, 18, A, 12. B, angle B and C are both 67, and angle A is 46. C is 9. 20 is about 5 centimeters. So it didn't say what to round to. And then this starts 8.7. Two is 37 degrees. You're trying to find the angle there, so you're using the inverse function. 4 is 900 meters. 6, 570,000 feet. 8, 176 meters. Questions on those? Okay, and then the review, I had posted the answers, but I want to go through and see if you've got any questions on them. So any questions from the first page of the review? $18. Okay, so I'm actually going to redraw this. Okay, so it gave you this, and it wanted QN, and it wanted PN. I'm actually going to put an X and a Y on there. X, Y. All right, so you've got that they're basically, this is a isosceles triangle because these are the same. I would know these are the same. It's an isosceles triangle with an altitude drawn. So what happens is it takes that 20 and it splits it into two congruent parts, which means this is 10 and this is 10. That gives you QN. Then you've got to focus on just one of these triangles, or 1/2 of your isosceles triangle, and it doesn't matter which one. If I know this is 10 and I want to find Y, I can use the 32. Y would be opposite. 10 would be adjacent, which means I can use tangent. So the tangent of 32 would equal Y over 10, and then numbers in the bottom, so I multiply 10 times the tangent of 32. Which is 6.24, and then I don't know what it said to round to. Nearest integer, so just 6. So again, that's a great SAT question. They're not going to give you a flat out right triangle and say solve it. They're going to make you apply a little bit of what you know, like in this one, the isosceles with the altitude that cuts that bottom part in half, and then the right triangle to solve the rest. Any other questions from the first page of the review? Okay, second page of the review. So 19 and 20 just wanted you to, wanted you to find the cosine, the sine, all that stuff. So you're setting up a ratio there of the sides. And then using C to solve, or using the last one, the inverse functions to find it. Everybody's good on this page? Yeah? Okay. All right, last one. Anything from the last page? $25 says the sides of the rhombus are 4 units long. One diagonal has a length of 4. How long is the other diagonal? Okay, so you've got a rhombus, right? 4, 4, 4, 4. And one diagonal is 4. It's asking how long the other one is. All right, so we just said that rhombus, the diagonals are perpendicular, right? So all of these are right angles. A rhombus is also a parallelogram, and a parallelogram, the diagonals bisect each other, which means that if this length here is 4, it's actually 2 and 2. So it'd be 2 and 2. Now you can focus on a right triangle, like in this one. You can use either of them, but let's say I just grab that bottom one. Here's my right angle. This is 2, this is 4. It wants me to find this, and then I would double it to get the other side length, or to get the entire diagonal. So I need to just use the Pythagorean theorem. I would get 2 squared plus x squared equals 4 squared. 4 plus x squared equals 16. X squared would equal 12. And x equals the square root of 12, which is 2 root 3. Does it ask you to keep it exact? Or let me see, hang on. 25. Yeah, okay. So then if that's half of it, I just multiply by 2. 2 times 2 root 3, which is 4 root 3. If it had asked for that, like rounded, I would do 4 square root 3 in the calculator, and I would get 6.9. So just pay attention to the format of your answer. That was one way. This way, remember, you'd write it as 4 SQRT for square root, and then 3. So now you're applying Pythagorean theorem with, again, your properties of rhombus, which is that the diagonals are congruent. I mean, not congruent, sorry. They are perpendicular, and they bisect each other. They would be congruent in the rectangle and the square. Questions? Anything else from this last page? All right, this is what we talked about on Friday. This was kind of like our reference sheet for chapter 8. It had everything that we needed to know on it. But then, of course, you have to know how to apply it. I'm going to give you guys, let's go 20 minutes. I'll give you a 20-minute break, just over 20 minutes. So at 9:10, you need to be back here, and you need to be ready to go to take your test. So you need to make sure that that second device is positioned far enough that I can see your workspace. You need to make sure that you have your calculators. And when you come back at 9:10, you can go right ahead. You can get your scrap paper ready. And then make sure you've got your calculator, scrap paper, notes, all that stuff ready to go. If you're going to use hard copy scrap paper, do me a favor and don't use front and back. Just use front. And then that way you can literally take a picture of both of them side by side. If you're using Notability and you're sending it as a document, that's fine. I don't care how you attach your work. You just want to make sure that you have enough space so that you can do it. All right, so 9:10, come back. Go get a snack, break, potty break, whatever you need. I'll see you in 20 minutes.
I just give Kathleen belly rubs, but it's not the same because she's a technique. Also, watch out for my elbow.
So, chapter 9, section 1 is just the basic terms. So, we're going to, like I said, talk about just circles for chapter 9, but a lot of stuff with circles. A lot of it's vocab. A lot of this is review. That's the good thing, like terms that you should have seen as early as elementary school. So, hopefully, this is review, but then we get into some application on it. So, the circle, by definition, is the set of points in a plane at a given distance from a given point in that plane. So if I start with just a single point in the middle, and then I go out the same distance in all directions, and then I were to connect all of that, that's a horrible circle, but you get the point. That would be the definition of the circle. So a set of points in a plane at a given distance from any given point in that plane. The center is that point that you're talking about. So the initial point where everything is equidistant from is your center. It's a point, so it just gets a capital letter. And the radius is the distance between that point and the outer ring on your circle. It's the segment that joins the center to a point on the circle, and the plural of radius is radii. So when we talk about more than one radius, it's the word radii. All right, some more definitions. A chord, a secant, a diameter, and a tangent. So a chord is a segment whose endpoints lie on the circle. So from end to end, it would lie on the circle. So it's going to pass through the circle, end to end on the circle. But it doesn't have to pass through the center. So it could be anywhere around the edges of the circle, which you'll see in a minute. There's a diagram to kind of show all this stuff. The secant is a line that contains the chord. So a secant, by definition, is a line. It's going to continue on past the circle. There is such a thing called a secant segment, which we'll talk about in a little bit. That would stop. But the secant itself is a line. The diameter is a chord that contains the center of the circle. So the endpoints are on the circle, but this time it passes through the center of the circle. And a tangent, again, a line. So it's a line in the plane of the circle that intersects the circle in exactly one point. So this only intersects the circle at one point. And that point is called the point of tangency. All right, so this diagram just puts it all together. Obviously, we've got a circle. This segment here that goes end to end, so this end points on one part of the circle, this end points on one part of the circle, is called a chord. If my center was here, so let's say this is circle C, then this is the diameter, which by definition is a chord. The end points are on the circle, but it passes through the center. So a diameter is a chord. A diameter is always a chord sometimes a diameter. The secant is the one that passes through the circle on both sides. So notice this is a line. It's got arrows on both sides. It's going to hit both sides of the circle and continue on past to go outside the circle. And the tangent, which is also a line, it's outside the circle. It only intersects the circle at exactly one point, and that point is called the point of tangency. So the word tangent has like 7 different definitions. This is obviously different from the tangent as in SOHCAHTOA tangent, right? This is just the name of that line. And like I said before, sometimes you'll see secant segment, which would mean instead of having arrows, it's got endpoints like that. They could be on both sides. It could be one endpoint and then one endpoint as long as it's outside the circle. So a secant's always going to go outside the circle. And then a tangent could also be a segment. Tangent segment would have endpoints here. By definition, their original names are lines, but they can have the word secant segment or tangent segment, which you'll need when we get to the theorems at the end of the chapter. Questions on those? So A sphere is a three-dimensional circle. Okay, it's got center O. And the radius, again, is the set of all points from the center to the sides, but this time it's at the sides of the sphere. So this can be to the right, it could go backwards, it could go up, it could go forward diagonally. All of those segments are all going to be the same distance. It's just your 3D circle. So a sphere is like a basketball, a tennis ball, a volleyball, a soccer ball, a globe. An orange. All right, so this is one way you'll see those applied. It's going to ask you to name each of these. Like, what are each of these? The alignment on these is off, but just picture them to be underneath it. It says point O is the center of the circle. Name each figure. So I'm going to unmute you so that you talk back to me so I don't have to have all these answers by myself. Okay, so if I'm looking at OM, notice this is segment OM. OM would be here. What's the best way to describe that type of a segment? What type of segment goes from the center to the side? So close. Half the diameter, right? Which is radius. Good. Then you've got MN, again, segment MN, so it's going to be the segment that goes from N to N, stopping at those points. What's the best way to describe that? Yep. Then you get line MN. So this is going to be where it goes through M and N and continues beyond the circle. It's not a chord anymore, right? Because it continues on beyond the circle, which means it's a what? Good. Okay, then we get segment MQ. So MQ goes from M to Q, stops at M and stops at Q. What's the best way to describe that? I'll give you a hint. There's two answers to that one. It's a diameter. It's also a chord. So we say the best answer is diameter. If it's a chord that passes through the circle, passes through the center, we say the best way to describe that is it's a diameter, okay? It's not technically wrong to say that's a chord. By definition, it is a chord. But if you want the best answer, most specific answer, then you want to use diameter for that. Okay, then we're at ML. So ML, ML, segment ML is here, which is outside the circle, but it hits at one point, which makes this what? Tangent. So look at E and look at F. E, segment, F, same exact name, but it's got a line over it this time, right? So the tangent, when it stops, is called a tangent segment. The tangent, when it doesn't stop, when it has arrows, is just called a tangent. So E would be a tangent segment and F would be a tangent. And then point M is called what? Good. So O is a point. O would be the center. M is a point. It'd be the point of tangency. Good so far. So remember, tangent and secant by definition are lines. Tangent segment stops. Secant segment stops. All right, so A says name a tangent to sphere S. How would we name the tangent to sphere S? So which of those two lines is outside the sphere and only touches it at one point? PQ or TU? TU. And because it's tangent, we call it line TU. So it could be line TU or line UT. But it has to be a line because it didn't say segment. B says name a secant and a chord of the sphere. So what's the secant of the sphere? Good. Line PQ or QP, but it has to be a line. What's the chord of the sphere? What's the difference between the secant and the chord? Does a chord go outside the circle? No, so the chord stops, right? Which means I can go from P to Q, but it's a segment. Which means you can have the bar over it, but you don't need it, right? A segment could also just be PQ. You don't need the bar over it. And then C says name two radii of the sphere, and it says hint, they're not drawn yet. So sometimes you got to get creative. How could I name a radii of the sphere? There's actually 4 options you could use. You can go from R to S. Yep, that's one. US, that's another. There's 2 more. Say it again. QS. Yep. And the last one. Good job. So from any point on the sphere to the center. Questions on any of those? All right, congruent and concentric circles, so some more definitions here. Congruent circles are circles that have congruent radii. So any circle that has a radius of 5 would be congruent to each other. Any circle that has a radius of 10 is congruent to each other. So as long as they have the same radius, they are congruent. Concentric circles are circles that lie in the same plane and have the same center. So the picture that's here, these are concentric circles. It's almost like a bullseye or a dartboard where you see the rings moving out. They both have the same center and they overlap, but they're not necessarily the same size. Okay, inscribed and circumscribed. So a polygon is inscribed in a circle if each of the vertices lie on the circle. So think inscribed is like inside. If the polygon is inside the circle or whatever, because it doesn't necessarily have to be inside a circle, but it's inside and the vertices are on the circle, then it's inscribed. So this triangle is inscribed in the circle. And the one on the outside is said to be circumscribed. So inscribed is inside, the one on the outside is circumscribed. So in this case, the circle is circumscribed about the polygon because the circle is on the outside of the polygon. Now this can actually be reversed. Let me see if I could do the... So if that's my circle, I can also have a triangle inside the circle. Wait, sorry, just did the same thing. I can have the circle inside the triangle. Okay, so picture that not overlapping as much, but that the circle is actually on it like that. And now I would say that the circle is inscribed in the triangle. And triangle is circumscribed. About the circle. So the one on the inside is inscribed, again, inside, inscribed, and the one on the outside is said to be circumscribed. You're not really going to be like tested on this, but sometimes it'll tell you like a triangle is inscribed in a circle, and you have to draw that. So you have to know by the word definitions of those words what that means. Again, this is now 9.2. So theorem 9.1, which the actual number means absolutely nothing. It just means it's the first theorem mentioned in chapter 9. But what it says is what's universal to geometry, and that's what's important, right? If I took this theorem and put it in another book, it might not be called theorem 9.1. But it does say the same thing, which is if a line is tangent to a circle, then the line is perpendicular to the radius drawn to the point of tangency. So perpendicular to the radius, tangent, perpendicular to the radius. And perpendicular means what? If two lines are perpendicular, they form at what? Good, a right angle or 90 degrees. So when you've got a tangent line like this one and a radius like this one, then they meet at a right angle. Both of those would be 90 degrees. Okay, the corollary, which is something easily derived from a theorem, says the tangents to a circle from a point are congruent. So I call this one like the ice cream cone corollary because it looks like an ice cream cone, right? Like here's my cone, and then there's my ice cream scoop. Okay, these two are congruent. So if it comes from the same point on the outside of your circle, and they're both tangent, notice that those don't cross through the circle. They have to go to the outside of the circle. If they're both tangent, then they're congruent. Anybody still coming that one down? Okay, theorem 9.2, back to the tangents and the radii. This is the converse to the first one. Now it says if a line in a plane of a circle is perpendicular to the radius and its outer endpoint, then the line is tangent to the circle. So now we've flip-flopped the if and the then. We're saying if it's perpendicular, if I know this is a right angle from the get-go, or I know that it's perpendicular by a statement like AB is perpendicular to BC, then I can say that AB is the tangent to this circle. Anybody still coming that one down? All right, here's some application. So it says if OR is equal to 6, oh, and this needs to be a tangent. So the hardest part, to be honest, when I make these PowerPoints is like to get this little spot to be exact is so hard. This is tangent. This is only intersecting it at one line, at one point, okay? So it says if OR is 6, that means that this is 6, and OT is 8. Then RT is what? So it wants to know this whole side here. So if OT is tangent to this circle, what other piece of information do you know just by knowing that it's tangent? Good. So this is now a right triangle, yes? How do I find the third side of a right triangle if I'm given the other two? Pythagorean theorem, or I get lucky and it's a triple, right? Which is in this case. My triple is 6, 8, 10, so RT is 10. If you don't know the triples, then you work through it. 6 squared plus 8 squared, 36 plus 64 would be 100. Square root of 100 would be 10. But knowing your triples definitely saves you time. So that's the first part. Then it says, separately from that, that OTR is 45 degrees and OT is 4. What's RT? So now I got a right triangle. One angle is 45, which means the other one is also 45, right? Even if it's not drawn to scale, which a lot of these won't be. So here's my A, here's my A, here's my A root 2, which means x's. Plug that 4 in the place of the A and you get the answer would be what? Good, 4 root 2. So now we're taking all the stuff you just learned about right triangles and we're plopping them inside circles. I told you it's not going anywhere. Right triangles aren't going anywhere. All right, a common tangent, another vocab term, is a line that's tangent to each of two coplanar circles. So again, remember I told you this is really hard to get exact, but that should be a line, a point that literally touches the outside of that circle. So this line here is called a common tangent because it's tangent to two circles. Okay, there's two types of common tangents. One's internal and one's external. And the test for it is this. If you draw a segment connecting the centers of the circles and the tangent crosses through that segment, then it's called an internal tangent. If when you draw that segment and the tangent does not cross through it, then it's called an external common tangent. So if you could picture this, if I were to take and just connect my two centers, so if I did this to this and I did this to this, okay, connected a segment that connected the two centers, if my tangent doesn't cross it, which is this first one, then this is a common internal tangent. If it does cross it, like this one, then this is a common oh, nope, that's reversed. Sorry, hang on, this is external. If it doesn't cross it, it's external. And if it does cross it, external. I think I said it wrong too. If it doesn't cross it, it's external because it's outside. And if it does cross it, it's internal. So that switched. Hang on. I'll correct it and then we'll go back to it. Okay, tangent circles. Two coplanar circles are tangent if they intersect the same line at the same point. So again, this is kind of hard. You got to picture that it's this. And then this would be right up against it. These are both tangent circles. They can overlap. So they both intersect this line, let's call this AB, at one point. Okay, they both intersected at this point here and this point here, which means these are both tangent circles. Intersect at one point. All right, example 2, name a line tangent to circle P but not circle O. So we're looking at this diagram and we want to find something that's just tangent to circle P, which is this one. That would not be tangent to circle O. So tangent to circle P would be OB this line here. It would be AE this line here. And it would be CD this line here. So all three of those are tangent to circle P. Now we want one that is not tangent to circle O, which means I'm talking about OB or BO. That would be a secant to circle O. B says name the common external tangent to O and P. Okay, so we need it to be a common tangent, which means not OB. Let's erase that one because we just said that that would be tangent to the first one but not the second one. Which means that we're looking at the two common tangents of AE and CD. And we just said that if we took a segment and connected the two centers, that the internal is going to cross through it, the external does not cross through it. So if I want an external tangent this time, I'm looking at CD. It does not cross through the segment that's connecting my centers. Or DC, the same thing. C is a common internal tangent. So internal is the one that crosses through that coordinate, that segment that connects the two centers. So this would be AE. So E is kind of like that point right there. Questions on that one? So again, remember external, it doesn't intersect it. Internal, it does, which is the reverse of what that said, which I'm going to correct, but just make sure you've got it right in your notes. Okay, example 3 says circle M and circle N are tangent at point P. So here's my point of tangency, point P. PR and SR are tangents to the circle, so this should really be right on there. And circle N has a diameter of 16, PQ is 3, and RQ is 12. So there's a lot going on here. The first thing hopefully you read when you're seeing that PR and SR are tangents are that these two segments would be congruent. That's that ice cream cone corollary that says that this would be congruent to this. Those two would be the same thing. Then it says it has a diameter of 16. So I don't even have a diameter drawn. But if I did, it would be 16. PQ is 3. And RQ is 12. So I would say probably the easiest thing to figure out is that PR, which is one of the questions, is 15. Because you just got to add those two together. And RS would also be 15 because of that ice cream cone corollary. Now I got to break apart all the other information. If my diameter is 16, what's my radius? 8, which means NS is 8 and NP is 8. So NS is one of the questions too. You okay, bud? You okay? Okay. So if the diameter of my small circle is 8, what's the radius of that small circle? 4. Now that's MP. Now I need two things. I need MQ, which fills in this triangle here. What did we say is true about a tangent to a circle? It forms what kind of angle? Right angle. So I actually have a right triangle in here where one leg is 3 and one leg is 4. This one was 4, which is another triple. My hypotenuse would be 5. So NQ is 5. And then the last thing I need is NR. So if this is 15 and this is my right angle, I've got another right triangle here. This one here. Where the leg is 8, the leg is 15, and the hypotenuse is what I'm looking for. That's another triple. And it's 8, 15, 17. So there's a lot going on in this one example. You probably don't get a test question that has quite that many things, but it will have parts of it. You're either going to see the ice cream cone one where you've got to make those equal to each other, or the right triangle with the tangent, or any kind of application of that stuff. Questions? All right, if you want to get like all right, I'm going to just start because I don't want us to run over too much. So 9.3 is arcs and central angles. So we're going to talk about two things. One is like how to name and stuff like that, these arcs, and these central angles. So you've got angles on the inside of the circles and then chunks of the outside of the circle, which are like the crust of a pizza pie, if you could think about it. Those are called arcs. And then we're going to eventually learn to talk about like the measures of each of these. So we start with, what is a central angle? A central angle is an angle with its vertex at the center of the circle. By the end of the chapter, we're going to have like, I think 7 different types of angles. So it's important to keep like track of which one is which. Central means that the vertex is at the center, okay? So it's got a point literally at the center of your circle like this one. And then the sides of it are both radii. So this is a radius, AB is a radius, BC is a radius. That's called a central angle. So if you like could cut a piece of pie, right? That angle that's formed by the tip of the pie, that's called a central angle. It's going to have 3 letters. You can't name it with a single letter because the vertex is shared, right? So in this case, angle ABC is one of the central angles of a circle. There's lots, but that's one of them. Oh, thank you. Minor less than half. Semi is half. Major is bigger than half. All right, so if we're looking at the difference between minor semicircle and major arc, we name arcs, if they're if they're minor arcs, you can name them with 2 letters, the endpoints of the arcs. So something like AC, okay, would be that little curve right there. And it's a minor arc because it's less than half the circle. Semicircles and major arcs need 3 letters. And they go in that order. So if I said D, then A, then C, then I start at D, I hit A, then I go to C. So that's a semicircle because it's exactly half the circle. And I know it's half because this is my diameter. So the diameter cuts it into those halves. And then arc DAC again goes in that order. So I go from A to D to C. A to D to C. And that's a major arc because it's bigger than half. Another major arc could be like ACD, so that could be another major arc. Or I could go CDA, that's another major arc. So there's a lot of different ways to use these letters, and the order of them is super important. You got to hit them up in that order when you're moving around your circle. Whether you go clockwise or counterclockwise doesn't matter. but you have to hit them in the order that they're going. So minor can have 2 letters, everything else has to have 3. So the measure of an arc is equal to the measure of its central angle. I don't know why that's so blurry. There it goes. So what's given to us in this diagram is that this angle here is 50 degrees. So if I want to know the measure of arc AC, it's equal to the measure of that angle, which means it's 50 degrees. Now, what do we know about a full circle? What's the degree measurement on a full circle? It's 360 degrees, right? Which means half of it would be what? 180. So a semicircle is going to equal 180 degrees. Full circle is 360. Semicircle is going to be half that, or 180 degrees. So the next one says A, C, D. I'm going to go from A to C around to D. We just said half the circle is 180, so from here to here is 180. And then we add on another 50. So to get A, C, D, I have to do 180 plus 50. That's a 230. Yeah. 230 degrees. And then arc CAD goes from C to A to D, which is the other half of my circle, or 180 degrees. If I were to classify these, this would be minor, this would be major, and this would be semicircle. Okay, adjacent arcs are just like anything that's adjacent. Adjacent means next to. Adjacent arcs would be arcs that are next to each other that have exactly one point in common. So if I have a circle and I had an arc that goes from here to here, and then an arc that goes from here to here, those are adjacent. They can't overlap. I can't say that this arc here is adjacent to the pink arc. They can't overlap, okay? It's got to go endpoint to endpoint, and they have to be next to each other. So those are adjacent arcs, arcs that are next to each other. Just like you had segment addition postulate and angle addition postulate, you have arc addition postulate, which is what we just used in the last example. It says the measure of the arc formed by 2 adjacent arcs equals the sum of the measure of those 2 arcs. So if I wanted to find the measure of an arc that combines 2 arcs together, I simply just add those 2 arcs. Congruent arcs are, if you think about the word congruent, right? Same size, same shape. Now we're talking about arcs. So these are 2 arcs in the same circle or in congruent circles that have equal measures. So every semicircle is congruent. Whether it's the 2 halves of an individual circle or you're comparing 2 semicircles in different circles, as long as those circles are congruent, okay? Not every, I shouldn't say every semicircle is congruent. As long as the 2 circles are congruent, so the radii have to be congruent, then the arcs are congruent. So same circle or in congruent circles that have the same measure. Okay, Theorem 9.3, again, no name, number's not important, but what it says is important. In the same circle or in congruent circles, two minor arcs are congruent if and only if their central angles are congruent. So if I had two circles or the same circle, it doesn't matter which one, so I've got two congruent circles here, right? And then I've got two arcs that as long as this angle is the same in both, the arcs are congruent. So AB would be congruent to CD and vice versa. If I didn't have the angle, but I did know that this was 90 and that this was 90, I would also know that the angles are congruent. So they're both the same. Like if and only if means switch it and it still works. They're congruent if the central angles are congruent, and if the central angles are congruent, the arcs are congruent. So this is how you'll see the like arc CD. It'll either say the word arc and then that, or it will have the little curve over it. All right, so this one says name two minor arcs. So if I look at this diagram, minor is less than 180, which means one of the arcs could be here, AR, arc AR, or arc RA. You can call it either one. And the other would be arc RC or CR. Name two major arcs, so now I needed to get bigger than 180. So if I start, let's say I start with R, I can go all the way back around to C. So R, and I can pick either A or D to name it. I can call it RAC, okay, or I could call it RDC, that's the same arc. I could also go the other direction, start with R, but wrap all the way around to A that way. And I go RCA or RDA. Those would both be major arcs because they're bigger than half the circle. Because this is my diameter, that divides it into two semicircles. So the first semicircle would be ARC or RCA, same thing. Second semicircle would be ADC or CDA. And acute central angle, think acute still has to be under 90. So this one appears to be 90 or bigger than 90, which means my acute one would be ROA. And two congruent arcs are arcs that have the same measure. The only one we know anything about are the semicircles. Those would both be 180. So ARC and ADC. I know,
Great.
All right, and then the last one, it says give the measure of each angle or arc. So now I've got actual values on these. The first one is arc WX. So WX is here. I don't have a value on that one, but I do know that this is 30. I know if this is 50, this must be 50, and here's my diameter. So all three of those have to add up to 180. If I add the 30 and the 50, I get 80. Subtract it from 180, and what's left is 100 degrees here, which would be the same as the arc. And that would be a minor arc if I was to classify it. WOT we already labeled, that's this one, which is 50 degrees. And arc XYT goes X, then Y, then T, which is gonna be this 180 plus this 30, which is 210. And that would be a major arc if I was to name it or to classify it. Okay, that's the end of 9-3. So that was 9-1, 9-2, 9-3. And then again, you need to work through that packet, okay? And then the 9-4, 9-5, 9-6, 9-7, I think it's in 2 parts, the videos. So again, like I said, 9 is rough because it's a lot of stuff, okay? And then tomorrow we'll test on chapter 9. But we will review the whole first part of class. You'll take your test at the very end of tomorrow. So we've got a lot of time to work on review for tomorrow. Actually, you know what? I'll even give you the first... I'll give you the first 45 minutes tomorrow to work on the end of packet 9, the second pack. So I would say go at least, like, watch the videos of all of it because you won't have time to watch videos while I teach. But then I'll give you the time to work on 9-6 and 9-7 if you want to save that. So I would do 9-1, 2, 3. That packet's going to be due at 8 a.m. But then the other packet I'll make due at 9. So you get a little bit of, or 8:45. You get a little bit of time in class tomorrow to work on it because it's a lot. Okay. Any questions for me before you go? Everybody good? All right, ladies. Have a good day. I'll see you tomorrow. Bye.